everyone. Welcome to Denoise. On this show, we talk about the latest AI/ML innovations, their implications, and their applications with the minds creating them. Whether you're an AI/ML expert, an enthusiast, or simply curious, this is your place to stay up to date on the technology that's shaping our future. We're talking LLMs today. Now, wouldn't it be cool if an LLM model could ingest entire scientific documents and accurately summarize them for us? Or conversely, produce a complex fiction series that maintains plot coherence. Anybody who has used ChatGPT or the like knows we are not there yet. So here to talk to us today is Jinghan Yao. He is a Ph.D. student from the Ohio State University specializing in high-performance computing and machine learning systems. And he's also worked for Microsoft DeepSpeed and Noah's Ark Computer Vision Lab. And he addresses in this paper precisely the challenges of resource constraints and cost constraints in training models on ultra-long context content. My question is, what does that mean? What does it look like when we figure this out? Now, the thing that came to mind for me, I'm an author. I just published my fantasy novel, Kiyakora, A Flame of Sorrow. Not to plug it here, but it is available on Amazon and drops in paperback on December 10th. If you like magic, mystery, a little bit of romance, and want to support, please do. I'd greatly appreciate it. But more to the point is it's the first book in a trilogy. And so an LLM model that can maintain coherence over the course of not only one book, but potentially several, have intricate character development, plot twists, all of the things that you're looking for in an engaging, immersive reading experience. I'm really interested in that. Could that happen if we can master training on ultra long context scenarios? And if it could, could the content be truly original? If it could be truly original, if it's just merely influenced by training data. Is that so different than what artists, authors, musicians do now? Aren't we all kind of influenced by the things that have come before us and sort of our own real world training data? So if it could produce something truly original, how would we have to think about creativity? What would happen to authors? Would there be authors? Would we just be like prompters now? I'm curious what you all think on how we might have to think about creativity differently in the future, whether authors are on the verge of extinction. I don't know. Drop it in the comments. I'm really excited to talk to Jinghan Yao about the potential of ultra long context training on large language models. Thank you, Jinghan, for being here to talk to us about your paper. Before we dive into the details, though, I want to get a sense of your journey into machine learning and into this space of large scale AI training and inferencing specifically.
Yeah, thanks, Allison. Actually, it's been quite an interesting journey to get here. So it was like back in my second year of undergrad. So I was doing research in computer vision and visual question answering. It's like giving a computer an image along with a question, and it figures out the answer by analyzing the image. So it was really fascinating to me at that time. So I remember that I published my research paper on that topic right before my graduation. And interestingly, so that paper caught the eye of Professor John from the University of Oxford. So he found it really intriguing, and so he reached out to me so to see if I would be interested in working with him in his new lab at Fudan University. So I thought, like, why not? So it aligned perfectly with my interests and in computer vision. So around that time, transformers were becoming a big deal in AI. So everyone started to dive in that. But applying transformers to computer vision was pretty challenging because of their high computational complexity. So we set out to design an algorithm that could significantly reduce the transformers workload. And that work ended up being spotlighted in at Europe's 2021. And it was through that project that I realized, okay, I'm really passionate about making AI or machine learning models run faster. That's very simple. And that led me to pursue my PhD here now in high performance computing, where I continuing to explore ways to make AI models more scalable and efficient.
Great. And so that kind of links probably to your motivation behind this specific paper. But yeah, talk to us a little bit about the specific motivation and the problem that the paper addresses.
Thanks for the question. So actually, it began with a very simple question. So how can we train these powerful language models more efficiently? So in the AI community or any other field that use AI, so there is an urgent need to control the budget, like the money issues. So even just for those inference workloads, like we're talking about training inference, multiple phasings, right? So these models are now like they are already trained by those large companies, institutions, right? But deploying them in production often requires what we call as fine tuning. So that's where want the model to adapt to a specific area or like a domain of knowledge that you are interested in. But the thing is, even for the fine tuning, they are just simply too expensive and resource consuming. So they require a huge amount of hardware, tens of hundreds of GPUs. And even for big companies, that's not an easy job. Among all the fine tuning tasks, handling the long context thing is the most challenging one. So previously, we were feeding the model with only like hundreds or thousands of tokens. But now we're talking about feeding it millions, so there is a huge gap between them. And for researchers who need to control their budget, like using a single compute node with 4 GPUs or 8 GPUs, previous methods just weren't feasible because they typically require hundreds of GPUs. In our paper, what we proposed is called FBDT, or like fully pipeline distributed transformer. We achieved like 2 million context lengths with only 4 GPUs. So this was totally infeasible using the previous solutions. So basically, we extended the maximum supported length by 8 times, and we also achieved a very good hardware efficiency. Our motivation was really about making these advanced language models more accessible and efficient for everyone, not
Right.
just those with massive computational resources.
Right. Making the technology more ubiquitous, allowing
Exactly.
more people to engage with it. So you gave us a little bit of insight into the paper, but before we dive deeper into the details, give us just an overview of your methodology, the experiments that you set up, and then the empirical findings.
Yeah, sure. So previously, because I like to start with a comparison with the existing solutions, like why you need our solutions instead of using
Mhm.
the existing ones. So previously, when researchers wanted to train those language models with very long context, they try to expand the number of GPUs they use. So you see, if a single GPU memory is limited, let's say it can hold hundreds or thousands of tokens at a time. So when dealing with millions of tokens, the idea was, okay, why don't we just distribute the workload across more GPUs, right? Each GPU still handle like hundreds or thousands of tokens, but we can increase the total number of GPUs. And we can keep doing that until like we can eventually get the job done. So
Right.
methods like ring attention and the DeepSpeed Ulysses, Megatron SP, they're all using this kind of idea concept. But this method comes with two significant problems. So first is what we call as the scaling efficiency, right? You add more GPUs, the more time it's going to take to transfer data between those GPUs. So it's starting with like one person doing the job, and then you bring in 1,000 people. Sure, like the workload is distributed, but now those 1,000 people, they need to coordinate. And
Right.
this can introduce a huge amount of overhead. In this case, and in the model training fields, this coordination requires high bandwidth networks. So how you connect all your GPUs or your machines, and these networks themselves are very expensive. So they are even more expensive than the GPU itself. So makes everything even more inaccessible for researchers, right? And the second issue is what we know as the resource scaling. So every time you double the context length, you need to double your GPU resources. For example, if you are using like 100 GPUs to train a model with, let's say, 16K context length, and now you decided to move to 128K context length. What you do, you will need another 100 GPUs. So this
Okay.
is just not practical, and it's not cost effective. And even for those companies like large organizations, it's not very good. So in our early experiments, we realized that the main bottleneck in training those long context language models is what we call as the activation memory. So it's like think of as a piece of the component where you have in training. So it's like writing a book. So you develop a chapter by chapter, page by page, and every time you come up with something, you write it down instead of trying to keep everything in your head because it's just too much to remember. Similarly, GPUs are great at processing information, but they have limited memory for storing those information. We thought, why not offloading some of this stored information to CPU memory from GPU to CPU? So modern computers and supercomputers, they have CPU memory that's 5 to 10 times larger than the GPU memory. And plus, the CPU memory is much cheaper and more readily available. And by moving the processed data, those activations, from GPU to CPU, we free up GPU memory to handle more computations. But of course, there are some challenges in doing this. Transferring data between GPU and CPU introduce latency. And yeah, in some cases, it can significantly slow down the training. So the key was or like the hardest part is to design a system that can hide this kind of latency and keeps the GPU working efficiently. Our methodology differs from previous approach by, let's say, we reducing the reliance on a larger number of GPUs
Mhm.
or expensive high bandwidth networks. Instead, we use the existing CPU memories in those machines to handle the activation memory, the storage of those activations, and making the long context training more accessible and cost effective. But as I mentioned, so you have to consider the how do you hide those latencies between CPU and
Right.
GPU. So that's the challenges. I would say the main challenges of paper. Yeah,
Okay, so DeepSeed Ulysses and Megatron SP, those are two memory efficient techniques that are used and they operate on this sort of distributing the workload over multiple GPUs. You also mentioned at the beginning of the paper flash attention as another technique that you also build on. Tell us what flash attention is and how you build on it in this paper.
sure. Yeah, thanks. So when we talk about transformers, like how powerful they are, we also need to consider their compute and memory complexities. During training, we usually feed the model an entire sequence of or context, right? Let's
Right.
say this sequence has a length of n tokens, like n words. One of the key components of transformer is the self-attention mechanism, like the attention thing, right? So this part calculates the relationships between each pair of the words. So it's trying to find out the relationship between those words. And so if we have n tokens, n words, we are actually computing n squared pairs because each word has to interact with all other words. So that gives us n squared pairs because we are considering all the possible combinations. And this leads to what's called an O(n) square computational complexity. O(n) square is like more as a terminology in computer science. But it's not just about the computation. Memory is also a very big factor here. Before techniques like flash attention came along, we had to store some intermediate results when we compute the attention. And because there is no way to bypass that. And this memory itself also requires what we know as O(n) squared complexity. So you need O(n) squared both in compute and memory. So it's really hard. So flash attention made a significant improvement by reducing the memory requirements from O(n) squared to O(n), basically from the square to a linear requirement. So this is a very huge and significant improvement because now the memory needed grows linearly with the sequence length. So previously it was squared increasing, but now it's linearly. So it's much smoother, much lighter. However, even with this linear scaling, there is still a catch. So when we say something is like O(n), or like the complexity is O(n) or n, we are talking about how the memory scales with n in theory. But in practice, there is a constant factor involved. For example, 2n is on, 8n is still on. So you see there is a factor come before this n. But in theory, they are all on. But in practice, of course, 8n requires 4 times more memory than 2n, for example. So yes, in the case of flash attention, we found that this constant factor that comes along with n can be very high. So it can go up to 8. So which means that for every unit of the context, it requires 8 units of memory. So there is a 8 times relationship. So even though the memory grows linearly right now, the actual amount of memory required is still quite large, like 8n, right? And this becomes a significant burden in our experiment, especially when we're dealing with very long sequences, single millions of tokens, and times it with 8. So that gives you a huge amount of spike in memory. The flash attention and some similar techniques, they made strides in reducing memory usage. More is needed when scaling up to extremely long context due to these constant factors. Yeah, it's a non-trivial burden on memory, particularly with limited capacity of GPUs.
Okay. So moving into kind of the design, you talk a little bit about combining DeepSeed Ulysses with Zero Three. Tell us about why you did that and how do they work together?
Sure. This is a good question. When we're training models across multiple GPUs, multiple nodes, there are several ways to distribute the workload to optimize memory and performance. So before we talk about DeepSpeed Ulysses and Zero, we first briefly introduce the 4 main components that occupy GPU memories during training. So in short, they are like model weights, optimizers, gradients, and activations. So 4 components. All we need to know is that the zero technique, specifically zero three, it is designed to partition or distribute the first 3 components, the memory weights, optimizers, and gradients. And it will distribute these 3 components across the GPUs, which means that basically it creates shards so that the memory requirements for each GPU is like smaller than without it. So this method was originally proposed by the DeepSpeed team at Microsoft, and it is widely used because it just helps reduce memory usage and allows us to train larger models efficiently. But as we said, there are 4 components, right? So zero 3 only partition the first 3. So here's where Ulysses come into play. So Ulysses is designed to partition the activations, which is the last components in training. So combining zero 3 and Ulysses, we are able to distribute all 4 components across the GPUs. And they complement each other perfectly. So zero 3 manages model weights, optimizers, and gradients, while Ulysses take care of the activations. So this combination, how do you say, allows us to achieve the best possible GPU memory efficiency during training. As long as the context is not too long, it enables us to train large models or use fewer GPUs without running into memory bottlenecks.
I might be going backwards here, but what is the difference between how DeepSeed Ulysses works and Megatron SP?
That's a great question. The simplest way to explain this would be if we consider a tensor in our LLM training. So let's say the tensor has 4 dimensions. The first dimension is the batch. The second dimension is like the number of tokens, like how long your sequence is. And the third dimension is in transformers, we use the term multi-head attention. So you have multiple attention heads, right? Each
Mhm.
attention head has its own dimensions. So the third dimension of the tensor would be the number of head. So let's say we use 16 heads. And the fourth dimension or the last dimension is the hidden dimension of each attention head. The difference between Ulysses and Megatron is along dimensions. So for Ulysses, it partitions along the number of head dimensions. For example, if we have 4 GPUs and we have 4 heads, 4 attention heads, so Ulysses will put each head on each GPU. So each GPU is only responsible for 1 head of computation in dealing with this sequence. But for Megatron SP, it slices along the dimension channel, which is the last channel. They work like on different dimension of the tensor, but they are all sort of partition the tensor among all the GPUs. So I think that's the way of explanation that I can think of.
You detail the empirical performance in the paper. Share with us a little bit about what your findings were.
Sure, absolutely. So that's an important aspect of our work. So we conducted extensive experiments using some of the highly regarded large language models, specifically the latest Llama 3.1 model. So there is a 8 billion model and there is a 70 billion model, two variants. So yeah, let me break it down for you. So when we run Megatron SP and DeepSpeed Ulysses on just four GPUs, they were able to support a maximum context length of K tokens. It's impressive in its own, but with our proposed design, the FBDT, by leveraging some of the techniques that maybe we'll introduce later, we were able to push that boundary to up to 2 million tokens. That's an eightfold increase, as I mentioned before, over the previous state-of-the-art solutions. And similarly, when we scale up to the Llama 70 billion models, so really large models, and now we are using 32 GPUs, the existing methods can handle up to 1 million tokens, but with FBDT, we are able to extend this to 4 million tokens effortlessly. To put this into perspective, there is a very good example. Consider the very famous novel, the A Song of Ice and Fire series by George Martin, so which contains around 2 million words. So with FBDT, you can fit the entire series and even future editions into the model all at once. So imagine being able to analyze or generate content based on the entire book series without breaking them down into smaller parts.
So now when you're measuring performance, you're looking at GPU requirements, token length. Are you looking at accuracy or anything like that?
Yeah, sure. So I would say that this is a very good point. There are some methods like previously where they try to extend the maximum context length in sacrifice of some accuracy, right? They use some, let's say, mathematical approaches to reduce the memory, reduce the computation, but you also sacrifice some of the accuracy because you use methods like approximation, something like that. But in our design, the initial goal was we won't change any numerical precision about the results. So we want to keep everything perfect there. And we want to seek out another way to reduce the memory, which is the methods we propose in our paper. So to answer your question, no, we did not change any accuracy regarding the model because that's not what we want. We don't want the users to use our model but sacrificing the model's performance and accuracy. Yeah, that's our goal.
Okay. Because I guess maybe I'm missing something because it seems to me like one of the reasons behind this, right? If you are not training on long context, then when the model encounters long context material, the accuracy goes down,
I
right?
see. Yeah,
So
yes, yes.
I guess one of my questions is how are you gauging whether I know this primarily focus on the accessibility, reducing the GPU requirements and optimizing memory, but how are you determining whether training on long context does create models that can handle these and produce more accurate results, maybe hallucinate less, maybe provide less misinformation? Is that all related to this?
Yeah, yeah. So this is a good question. As you mentioned, so before our work or before the work of Ring Attention or Ulysses, what people did was okay. So we want the model to work on on context. Like we're giving it a lot of prompt, a lot of document during inference, right? But the model itself was not trained on those long contexts at the first place. So you see, there is a very large discrepancy between training and inference because the model sees totally different context lengths in these
Hmm.
two phases. And so previously, people had no way of bypassing it because it was just infeasible to train on those long context It just won't happen. What people adopted by that time is they decided to use some extrapolation mathematical methods to force the model adapt to long context during inference. But of course, because the model was not initially trained on those things, the performance drops drastically. And in some cases where if the context was too long, you'll see that the model will simply collapse. So it will give you some nonsense outputs because it just cannot handle this long context.
Okay. All right. Got it. So, talk to us a little bit about the key innovations in the fully pipelined distributed transformer design that you introduced.
Mhm. Of course. So the key innovations in our fully pipeline distributed transformer or FBDT design are two things: trunking and CPU offloading. Remember how we mentioned about the memory consumption in flash attention, right? It can be up to 8 times the actual sequence length. If we let the GPU process the entire sequence at once, it's gonna create an extremely high memory spike. It's essentially 8n. That's a very high spike if you draw that out, where n is the sequence length. This spike can easily, solely cause out of memory issue on your GPUs. To avoid this, we implement a trunking mechanism. Instead of fitting the entire sequence to the GPU like all at once, we break it down into smaller chunks and process them one at a time, still using before. So the memory spike becomes totally manageable and fits within the GPU's capacity. So we process each these trunks sequentially until the entire sequence is handled. So it's like a for loop in the model.
Okay.
And the second innovation is the CPU offloading. Think of it in this way. So since the GPU is only working on one trunk at any given time, the other trunks, they don't need to occupy GPU memory. So they are not being processed yet. So we offload those inactive trunks to the CPU memory, and when the GPU finishes processing the current chunk, it fetches the next one from the CPU memory. So by doing this, we ensure that the peak GPU memory usage is controlled by the size of the single trunk, because at any given time there will only be one trunk in GPU memory. So regardless of the total length of the sequence, whether it's hundred thousands or like it could be millions, makes no difference. So this combination of trunking and CPU offloading allows us to manage memory much more efficiently. And it prevents those massive memory spikes and makes it feasible to train models with very long sequences without running into any GPU memory limitations.
Okay, and so this is when you get into the importance of finding the sweet spot for achieving optimal performance, considering the offloading and the latency. Talk to us a little bit about any trade-offs that you had to make and how you went about trying to achieve that optimal performance.
Sure. So that's a great point. So as we discussed earlier, so when the GPU is processing one trunk of the data, the rest of the trunks are stored in the CPU memory. So once the GPU finishes processing the current chunk, it will fetch the next one from CPU. That sounds straightforward, right? But here is the challenge, because transferring data from CPU to GPU takes time. So if the GPU has to wait for the next trunk to arrive from the CPU. Basically, it sits idle. We are essentially wasting those valuable GPU resources because they're not doing anything during that. So to tackle this, an intuitive strategy is to start moving the next trunk from CPU to GPU while the GPU is processing the current trunk. So these two things happens together. This way, we overlap the data transfer with the computation. So by the time the GPU finishes processing the current trunk, the next trunk is already there, ready to go. Make sense? Now, here's where the balancing act comes in. We want the time it takes to transfer the next trunk to be fully covered by the computation. No latency observed from the other side. This means the trunk size needs to be large enough so that the computation takes longer than the data transfer, right? But that's how you hide the latency of data transfer. But if the trunk is too large, it might not fit into the GPU's memory. So this is where we need to find the trade-off. If you simply make the trunk too small, like a very few tokens each time, then yes, you have a very good performance in memory spikes. You have no spikes in memory, but the computation itself happens too quick that your GPU is always waiting for the next chunk because the data transfer is slow at this point. The trade-off is between memory efficiency and the computational efficiency. So we need to find that sweet spot where the trunk size is large enough to keep the GPU busy and small enough to ensure that it won't exceed the memory capacity. So it's a bit of balancing act, and by tuning the trunk size, we can eventually achieve the optimal performance.
Okay. All right. So that makes sense to me. I'm thinking of auto scaling in the cloud, having the resources that you need when you need them, but not provisioning more than what you need and having them
Yes.
sit around idle. That's the connection I'm making. All right. So then tell us, and I want to get back to the chunk size in a second, but tell us a little bit about the double buffer design and how that helps maximize the GPU utilization.
Sure. So of course, so as we talked about earlier with this fetching or like prefetching, like we fetch the next chunk while we are processing the current chunk. This is what we call as prefetching. So the idea is to, like we mentioned before, do two things at the same time. To take this a step further or maximize efficiency, we use this is what we also call as a double buffer design, which means that you have to spare the space of two buffers. So that's how you can do two things at the same time. In our double buffer design, we allocate GPU memory for two chunks of data. While the GPU is busy computing the, let's say, the first chunk or the current chunk in the first buffer, the next trunk is simultaneously being loaded into the second buffer. So as soon as the GPU finishes with the first trunk, it can immediately switch to the next trunk because
Okay.
the next trunk is already there. And the GPU can perform this without any downtime. So no more idling. And this overlapping of data transfer and computation ensures that the GPU is always active, so never sitting idle waiting for data to load or something like that. By having two buffers, we effectively keep the GPU continuously busy, which significantly boosts the overall training efficiency.
Okay. So how do you determine the appropriate chunk size? Is it just trial and error that do you know where to start at least and then you can go
Yeah,
up or down?
yeah, thanks. So this is a very good point. So choosing the right trunk size is really pivotal for achieving optimal performance in our design. Through our research and experiment, basically the idea is that, so think of two, if you draw it in a plot, there are two lines. So finding the trade-off, finding the sweet spot is basically you're going to find where the two lines intersect with each other. So find that point that tells you what the trunk size is, because at that point those were when two latencies are at the same level, so that's how they can hide each other, or one can be hid by the other. So through our research and experiments, we found that a trunk size of 16K, yeah, 16K strikes the perfect balance. So it's large enough to fully utilize the GPU's computing capabilities, ensuring that all cores are actively engaged. At the same time, 16K is small enough to fit comfortably within the GPU's memory constraints. So preventing those out of memory issues we talked about earlier. So it was all about finding the sweet spot where we could keep the GPU fully engaged without overwhelming its memory capacity. And I think it's a key discovery for us as well in making FBDT both efficient and scalable.
You end the paper inviting researchers to collaboratively engage in long sequence LLM training. What do you see as the future work here?
Looking ahead, I do see several exciting directions for future work in long sequence learning training. First, the ability to handle long contexts. It truly opens up a world of possibilities of processing real-world complex prompts. Imagine applications like, as we talked before, the novels, those famous books, like historical books, and also some legal document analysis, scientific research. And with long context capabilities, LLMs can maintain coherence. I think that is very important, and context over much longer span of texts, so making them far more effective in these scenarios. And additionally, so combining long context training with techniques like RAG, the retrieval augmented generation, and chain of thoughts, so COT, and both techniques can be even more beneficial. So RAG enhances the model's ability to fetch and incorporate relevant information from vast database. And having a long context foundation model means it can handle more detailed and nuanced queries. So similarly, the chain of thought reasoning, so which improves multi-step logical processes. So it can also greatly benefit from the model's capability to retain and reference information over extended long prompts. So I would say this synergy allows for more accurate and sophisticated reasoning, leading to better problem solving and decision making chances. So overall, I would say the future of long context LLM training is incredibly promising. It's not only enhances the model's ability to handle extensive inputs, but it also amplifies their utility across various domains by enabling more sophisticated and context-aware applications, especially when you bring in RAG and COT. How can we combine them with long context training? Because for now, RAG and COT are both only used in inference. So nobody did it for training yet. So this is something I would say very interesting to explore.
Okay, so I'm thinking just from the end user, all the way removed from the experiments and from the training. You can upload a full document if you pay. You can upload a full document to like
Yeah.
Perplexity or something like that, and it'll, summarize it. You have to fact check it. It's not always accurate, but we're talking about potentially you could have, I don't know, it could ingest, to your point, legal documents, and we
Mhm.
could have something that can pull from relevant previous court cases and create really strong closing arguments and
Exactly.
reference legal precedents. Is that, and at your fingertips, like the world's best lawyer?
Yeah, that totally makes sense to me. I think one point you mentioned is about the problem with existing techniques, existing LLMs is about the hallucination. So I strongly believe that hallucination was because the model was not trained on long context effectively. See the when the model generates some output, let's say you are reviewing, like you wanted to output some legal documents, do some analysis summarization for you. The key is for the LM to accurately pinpoint the knowledge that it was looking for. For example, if you're asking for a specific date or a specific event, you want your model to actually find the knowledge in that date, in that event. So hallucination to me is the model itself cannot really accurately pinpoint the place where it need to retrieve the data. So it's like you have all the so sometimes the answer, the hallucination, the answer it seems to you as it plausible, it makes sense, but the if you check the correctness, it's wrong. So it looks to me it's more like you have all the right ingredients, the key ingredients, but they are from different recipes. So we are putting them together. It makes sense to me at the first glance, but further checking, okay, it just not make any sense. So I think, as you said, so extending the context during training can help the model to adapt earlier to those redundant information. So it can be trained how to accurately pinpoint the information it needs to retrieve. So along with, of course, along with a technique like RAG, which helps the LLM to even more accurately find the information for generation. Yeah.
The concern that LLMs in general have garnered recently about potential for misinformation, hallucination. What, in your opinion, you shared your thoughts on where you think that comes from and maybe how
Mhm.
to address it, but in your opinion, what are some of the ethical implications of this line of research and how we can collectively ensure that these models are developed and deployed appropriately?
Sure, absolutely. I think that's a really important topic. Hallucination is just one thing we talked, but for like bias or ethical responses, since are more complicated in these two domains. What I think is, I believe that the outputs generated by LLMs are a direct, from my perspective again. So it's a direct reflection of the data that they were trained on. So since these models are trained on diverse sources of, for example, books, newspapers, websites, blogs, etc. So they inherently carry the biases presented in that data. So
Mhm.
because we human produce those data, so this means we need to be vigilant about the biases that can emerge in the model's outputs. And again, for like this impersonation, so impersonation is another ethical concern, but it is different from the previous ones, like the biasings, because impersonation is more like you ask a model to impersonate someone, and it will respond from it with that one's tune or writing style. The model might mimic their writing style or voice. This can lead to, I say, like a fraudulent something like
Right.
that. Yeah, but I think this is where we need the human feedback, the human feedback mechanisms like the RLHF, reinforcement learning with human feedback, or the DPO, like the direct preference optimization. So this is where these techniques come into play. So we need model to know that what kind of responses, what kind of tunes might be like it's personating someone. So that's what we do not want. So in general, I would say that LLMs offers incredible capabilities, but we definitely need auxiliary techniques such as RAG or RLHF to make it more controllable and regulated.
As these LLM models become penetrate more aspects of our lives and are used in different domains and we rely on them more and more, do you think that there should be, for lack of a better word, quality metrics to ensure that these LLM models have to meet hallucination or accuracy or some kind of quality metrics before they're released to the general public?
Sure. I think this is a very important aspect as well. So first, for hallucination, so hallucination is all about how correct the answer that model output is. So we definitely have the metric to evaluate that because we can just compare with the fact that we have. And from my perspective, I do believe that hallucination can be somehow, I would say, eliminated with more advanced information retrieval techniques, such as the RAG, as we talked before, because it's all about whether the model can pinpoint the where it should retrieve the data, retrieve the information from. If we have a very powerful RAG or like an information retrieval system, it can perfectly assist the LLM to accurately find the information it wants. So I don't think hallucination will be a long-lasting problem. But for other ethical problems, such as the bias and related issues, from my perspective, I would say bias is really hard to define. So it depends on how we human perceive what is bias, what if the content output by the model is biased or not, because the model again was trained on those data that we feed to them. So there might be something that already hidden intrinsically in the training data. So the model is just a reflection of that. I do believe that for the bias issues, it requires more collective efforts from both the model side and our human side to because it's all about how we perceive it. So we need to work together to get to a consensus or to find a place where we are all comfortable with the LLMs being part of our life.
Okay. So tell me, I know I'm jumping around a little bit, but I want to go quickly back to the kind of broadly the paper. Have you considered how the fully pipeline distributed transformer design can generalize to other modalities?
Oh, okay. Absolutely. I think this is a fascinating area. So I firmly believe it can be generalized, and I know it can. I know several ways to achieve that. So, because at its core, so let's say other modalities, for example, vision and audio, right? Besides of language. So at its core, transformers operate by processing tokens. So for language, these tokens are naturally the words in a sentence, which are one-dimensional data fed sequentially into the transformer. Now, when we look at modalities like vision and audio, so we can apply a very similar token-based approach. So take image, for example. They are inherently like two-dimensional, right? But we can flatten them into one-dimensional sequence of pixels or patches. And this is exactly what many model vision models do today. So they're actually doing these things. And similarly for audio, the sound waves, they can be broken down into sequential tokens as well. And these sequential tokens represent different aspects of the audio signal. So everything can be tokenized. And as long as the data that can be effectively tokenized, our design FBDT method is applicable. So this means that yeah, whether we're dealing with text, images, or audios, as long as we can represent the data as a sequence of tokens, then FBDT can help manage memory and compute efficiency.
Great. So we've talked a little bit about the future of this work. What about for you personally, professionally? Do you have any papers coming up that we can look forward to? What are you working on now? Tell us a little bit about that.
Thank you. Yeah, I'm really excited about what's next. So as a researcher in high performance computing and machine learning systems, my main focus continues on making the training of large models even more efficient. So right now, training these powerful models can still take weeks or even months, which is significant challenge for most researchers. So my upcoming work will revolve around finding new ways to speed up this process and make it more resource friendly. So I'm looking forward to exploring innovative solutions that can reduce training time, especially, and make these models more accessible to researchers and organizations. But I will be more on the lower system level because that's what my PhD topic. And but I'm always interested in collaborating with others in the field to push the boundaries of these training LLMs. Just stay tuned for some exciting developments. Yeah,
Okay, great. All right. Thank you, Jinghan, for joining us and talking to us about your work. We appreciate your time.
thanks, Allison.